Modern aircraft rely on highly engineered braking systems to safely slow down, stop, and maneuver on the ground. But the technology behind these systems has evolved tremendously since the earliest days of aviation. In this video, we explore how aircraft brakes developed from simple mechanical friction methods to advanced multi-disc and carbon systems used in today's high-performance aircraft. By understanding how each type of brake works and why it is used, we gain a clearer picture of the engineering that makes safe aircraft operations possible. Early aircraft were built without brake systems and depended on low speeds, soft airfields, and the friction of a tail skid to slow down on the ground. As aircraft became faster, heavier, and increasingly operated from smooth paved runways after World War I, these primitive methods proved insufficient, making effective braking systems essential for safe ground operations. Modern aircraft rely on brakes to slow down and stop within safe distances, maintain position during engine run-ups, and in some cases assist with ground steering. The main wheels typically carry brake units, while nose or tail wheels usually do not. Reliable brake operation is vital for safe and controlled aircraft movement on the ground. Most aircraft use disc brakes, where a rotating disc is attached to the wheel and a stationary caliper applies friction to slow rotation. Depending on aircraft size, weight, and landing speeds, brake systems may include single disc, dual disc, multiple disc, segmented rotor, or carbon brakes, while older aircraft may still use expander tube brakes. Carbon discs are increasingly common due to their superior thermal and weight characteristics. Single disc brakes are commonly used on small, lightweight aircraft. A single disc is bolted or keyed to each main wheel so it rotates with the wheel. Braking occurs when a fixed caliper mounted on the landing gear axle applies friction to both sides of the rotating disc. Hydraulic pressure moves pistons within the caliper, pushing the brake pads or linings against the disc to slow the wheel. This pressure comes from the master cylinders connected to the rudder pedals, which activate the brakes when the pilot presses the upper portion of the pedals. Floating disc brakes use a caliper that straddles the brake disc, with multiple hydraulic cylinders built into the housing. Each cylinder contains a piston, return spring, and automatic adjusting pin. The brake linings are divided into two groups: the movable pucks attached to the pistons on the outboard side, and the stationary linings mounted on the inboard side of the caliper. Some brakes, such as the illustrated example, use 3 movable and 3 stationary pucks, but the exact number can vary with the design. The brake disc is keyed to the wheel and can slide laterally in its key slots, allowing it to float. When hydraulic pressure is applied, the outboard pistons push their pucks against the disc. The disc then shifts slightly until it makes contact with the inboard stationary linings, creating balanced friction on both sides and slowing the wheel. When the brakes are released, return springs retract the pistons to a preset clearance. The automatic adjusters maintain consistent piston travel regardless of lining wear. The adjusting pin also serves as a visual wear indicator, with the required minimum protrusion specified by the manufacturer. The caliper contains internal passages for fluid flow and includes a bleed port for removing air from the system. Brake bleeding must be performed according to the manufacturer's maintenance procedures. Fixed disc brakes ensure equal pressure is applied to both sides of the disc without allowing disc movement. Their design focuses on precise caliper alignment and piston operation to maintain consistent friction, proper wear characteristics, and reliable brake release without dragging. Dual disc brakes are used when a single disc cannot provide sufficient braking force. 2 discs are keyed to the wheel with a center carrier positioned between them. Brake linings on either side of the carrier contact both discs when hydraulic pressure is applied, and extended caliper bolts secure the assembly, increasing the total friction surface area. Multiple disc brakes are used on large and heavy aircraft where very high braking forces are required. These brakes work with power brake control valves or power-boosted master cylinders. The assembly uses an extended bearing carrier mounted to the axle flange, which supports key components such as the annular piston, a stack of alternating steel stators and copper or bronze-plated rotors, a backplate, and a retainer. The stators are keyed to the carrier, while the rotors rotate with the wheel. When hydraulic pressure pushes the piston forward, the entire disc stack is compressed, creating significant friction and heat to slow the aircraft. When the pressure is released, return springs pull the piston back. An automatic adjuster retains a preset amount of hydraulic fluid in the brake, ensuring proper clearance between the rotors and stators as they wear. Brake wear is checked using an external wear gauge. These brakes are commonly found on older transport aircraft. Because the discs are thin and do not dissipate heat efficiently, they can warp more easily. Segmented rotor disc brakes are advanced multiple disc brakes designed for the high heat loads of large and high-performance aircraft. Their segmented rotor construction improves airflow, heat dissipation, and resistance to warping, making them the standard brake type on modern air carrier and high-performance aircraft. The brake assembly includes a carrier or torque tube housing, actuating pistons, a pressure plate, an auxiliary stator plate, rotor segments, stator plates, automatic adjusters, and a backing plate. The carrier attaches to the landing gear and contains multiple hydraulic cylinders. Many designs alternate cylinders between two hydraulic sources so the brake remains functional if one source fails. Hydraulic ports and a bleed fitting are also part of the housing. The pressure plate, driven by the actuating pistons, compresses the stack of alternating stators and rotor segments. Insulating materials reduce heat transfer from the discs. Stators are keyed to the torque tube and carry replaceable lining blocks that help dissipate heat. Segmented steel rotors, keyed to the wheel, include slots or separated sections that improve cooling and allow thermal expansion. When hydraulic pressure is applied, the rotor stator stack is squeezed against the backing plate, producing the friction needed to slow the wheel. Retraction springs and auto-clearance adjusters pull components apart when pressure is released, maintaining proper running clearance. Whereas monitored using built-in indicators such as protruding pins or other manufacturer-specified designs. Some brakes use an adjuster pin, ball, and tube system to limit piston return and automatically compensate for lining wear. Carbon brakes represent the latest evolution in braking technology. Built from carbon fiber materials, they are approximately 40% lighter than steel brakes, significantly reducing overall aircraft weight. They withstand much higher temperatures, dissipate heat quickly, maintain structural integrity under extreme thermal conditions, and last 20 to 50% longer than steel brakes. The primary limitation of carbon brakes is their high manufacturing cost, though this is decreasing as technology advances. Expander tube brakes, widely used from the 1930s to the 1950s, use a fabric-reinforced neoprene tube placed inside a brake drum. When hydraulic fluid enters the tube, it expands outward and presses brake blocks against the drum to create friction. Springs retract the tube when pressure is removed, and some models allow clearance adjustment. Despite their effectiveness, their tendency to deform when cold, swell with heat, and leak eventually led to their replacement by disc brake systems. Aircraft braking systems have advanced from simple mechanisms to highly engineered designs that manage extreme heat and force. From single-disc brakes on light aircraft to segmented carbon brakes on modern airliners, each system is built for safety, reliability, and precise control. Understanding these systems highlights the sophistication behind modern aviation engineering. Thanks for watching.